Next, we're going to take a look at some problems that deal with Guy-Lussac's law. Okay, so Guy-Lussac's law is covered on slide number 12 in your PowerPoint. Okay, you'll recall this is where now we're having volume held constant. Okay, so Boyle's law had temperature constant, Charles's law had pressure constant, Guy-Lussac's has volume constant. Okay, and just as in Charles's law, we had volume and temperature directly proportional. In Guy-Lussac's law, we've got pressure and temperature directly proportional. Okay, so the first Guy-Lussac's problem is on slide number 13. You'll recall the formula. Initial pressure divided by initial temperature is equal to final pressure over final temperature. Okay, so again, these are directly proportional. So as pressure or temperature increase, the other will also increase, okay, because they are directly proportional. Okay, so our first problem on slide number 13 reads, a gas at 25.0 degrees Celsius in a closed container has its pressure raised from 1.50 to 1.60 atmospheres. What is the final temperature of the gas? Okay, so we're given 3 of the 4 variables. Okay, we're given our initial temperature is 25.0 degrees Celsius, but of course you know for gas law problems this needs to be in Kelvin. Okay, so you'll add 273, so we are at 298 Kelvin. Okay, our initial pressure is 1.50 atmospheres. We are increasing that pressure to 1.60 atmospheres. Okay, so we should anticipate that our final temperature, which we don't know, but we can expect it's going to be more than 298. Okay, so if we plug these values into our formula, we get 1.50 atmospheres over 298 Kelvin is equal to 1.60 atmospheres over our final temperature, which we do not know. Okay, so once again, just like you did in Charles's law problems for Guy-Lussac, we're going to again see this cross multiply and divide algebra strategy. Okay, so our final temperature is 1.60 ATMs times 298 Kelvin all over 1.50 atmospheres. Okay, when you do that algebra, again, atmospheres will cancel. We'll be left with Kelvin. Okay, and you should get 318 Kelvin, which is greater than our initial temperature, which is what we expected, right? Because our pressure was also being increased. Okay, so our next Guy-Lussac's law problem is on slide 14. Okay, and this one reads, a gas exerts a pressure of 900 millimeters of mercury at 20 degrees Celsius. What temperature would be required to lower the pressure to 1 atm? Okay, so we are having a pressure decrease, and they're saying what temperature would go along with that decrease in pressure. Okay, so recall our formula. Initial pressure over initial temperature is equal to final pressure over final temperature. Okay, and the information given in the problem, our initial pressure is 900 millimeters of mercury. Okay, like I said back when we did pressure with Boyle's law, please convert these to ATM. Okay, so you know that there are 760 millimeters of mercury in 1 ATM. Okay, so we are starting out with 1.18 atmospheres of pressure. Okay, our initial temperature is 20 degrees Celsius, but again, we need to get that to Kelvin by adding 273. So we are at 293 Kelvin initially, and they're saying, what if we decrease that pressure to 1 atmosphere? What would the associated temperature have to be? Okay, so just like we did in problem 13, plug these variables into your equation. P1 over T1 equals P2 over T2. Okay, set up the algebra to cross multiply and divide, and we get our final temperature will be equal to 1 atm times 293 Kelvin divided by 1.18 atmospheres, and we get 248 Kelvin. Okay, so once again, this is a good answer because we can see that our temperature decreased just as our pressure decreased. All right, so the next video will cover Avogadro's law. Yes, he does have a gas law. Okay, you know you're a good chemist when you get a number and a gas law. Okay, so Avogadro coming next. Stay tuned.